The exploding rotor tangled the radio frequency solenoid coil. To make a new one, a lot of questions emerged. First, how the original looked like. Second, what wire was used in the original coil. Then, of course, I had to figure out how to make the new coil and how to solder it exactly in the rotor spinning axis. The original coil is an EC or inductor, and as such the inductance is determined by the coil shape. These including the coil diameter, the wire thickness, the space between windings, the coil length and the coil material. I could find pictures of the original coil in the Bruker Solid System flyer. Another picture was available in a video on YouTube showing the stator and coil replacement of the exact same probe head. It has 6.5 windings and it is as long as the soldering tabs. The space between the rotor and coil internal should be minimal, but according to some papers, it is between 0.2 mm and 0.4 mm. The original coil thickness was 0.7 mm. Electron microscopic analysis showed that the coil is pure copper with gold and rhodium coating. I am really grateful to Dr. Krzysztof Kovac from the Institute of Materials Engineering at our university for these measurements. With the acquired information, I was looking for a coil parameter calculator to determine the space between windings, which turned out to be 0.5 mm. A tool was made for the winding job. On my self-made lathe, the brass rod was turned down to 4.4 mm thickness. A steel piece was inserted in the base, serving as a hook for the wires. Then I was just turning the tool in the lathe by hand while holding both wires. This way the thin wire made the desired 0.5 mm spacing. This spacer wire was wrapped from the gold-plated coil windings. The coil positioning was done by some spacers. Two 4 mm cylinders from polyoxymethylene and a 4.4 mm longer cylinder from Teflon were turned, both having a 2 mm hole in the middle. The two smaller spaces go into the bearings. The 4.4 mm spacer goes in the coil. Then a 2 mm drill rod was inserted carefully through the three spaces. This made sure that the coil is evenly spaced around the rotor axis. The coil ends were bent to the soldering positions and were cut to length. Small pieces of solder was added to both soldering holes. The original coil was soldered in 2 mm holes. Old solder was drilled from the contact tabs. The stator is a glass-like material, and as such it is very sensitive for temperature gradients, so I used a makeshift soldering stand from copper to transfer heat to the contact tabs. I was checking with a small piece of solder on the contact tab when the solder melts. Another indication is the color oxidation of copper, which begins at around 300 C, the same as the solder melting point. Cooling was done again through the copper tabs. This is a picture of a sample tuned for the proton frequency. And this one is tuned for the carbon-13 resonance. This is a comparison of carbon-13 spectra before and after the repair of a standard sample that was available. Overall, the repair took 1 month and the material cost was about €50. The most expensive was the gilded copper wire for 20 quids for 14 meters from England. It is not shown in the video, but I had to buy 4 by 2.4 mm polyurethane air hose and varnish tube to repair the sample eject hose. It took 1 week to figure out the proper sizes of copper crimping rings to mount the varnish tube. Thank you for watching.